Learn like a pro.
All right, class, welcome. In today's explainer, we're going to jump right into the chemistry of bases and alkalis. Let's break down the core concepts you absolutely need to know to really nail this topic.
So, here's what's on the agenda. First, we'll get our definitions straight. Then, we'll check out their properties, dig into the big difference between strong and weak, watch a chemical reaction happen, and then we'll wrap it all up with a quick recap. Sound good? Okay, first things first, let's tackle something that trips a lot of people up. What is the actual difference between a base and an alkali? They sound similar, but they're not quite the same thing. So, let's start with the big picture. What's a base? Well, you can define a base by what it does. It's basically a substance, usually a metal oxide, that reacts with an acid to neutralize it. And when that reaction happens, you're always left with just two things, a salt and plain old water. And here's the key takeaway, the one thing you really got to remember. All alkalis are bases, but, and this is a big but, not all bases are alkalis. So what's the difference? It all comes down to one simple thing, solubility. Can it dissolve in water? If the answer is yes, then that base gets to be called an alkali. And that's when the magic happens. It releases those super important hydroxide ions. This equation right here, it shows you that process perfectly. You start with a solid base, sodium oxide. You add some water, and boom, it dissolves and becomes aqueous sodium hydroxide. And that's our alkali. See those little letters in the parentheses? The S for solid turns into AQ for aqueous. Aqueous just means it's dissolved in water. And that very act of dissolving is what makes it an alkali. All right, so that leads to a pretty important question, right? How can you tell which bases are going to turn into alkalis? And once you have an alkali, what does it, look like, feel like? What are its properties? Let's dig in. The rules for this are actually pretty straightforward. If you want to know if a base is soluble, you just have to look at what metal is in it. If it's a group 1 metal, like lithium, sodium, all those guys in the first column of the periodic table, it's soluble. Same goes if it has the ammonium ion. If it has one of those, it'll dissolve and, you guessed it, become an alkali. Just about every other metal oxide? Nope, insoluble. So once you've got an alkali, there are a few telltale signs. First, they tend to feel kind of soapy. And there's a cool reason for that. They're actually reacting with the oils on your skin in a process called saponification, which is literally how soap is made. Then there's the classic test. They turn damp red litmus paper blue. And because they release all those ions into the water, they can conduct electricity. But a word of warning, you've got to be careful with these, because a concentrated alkali can be really corrosive. Okay, now we're getting to the absolute heart of this topic. We know what an alkali is. But what's the deal with calling one strong and another one weak? This right here is a classic exam question, so listen up. The answer has nothing to do with how dangerous or corrosive it is. It all comes down to a single chemical process called ionization. Let's think about it this way. In chemistry, strength is all about how well something does its job. For an alkali, that job is releasing hydroxide ions. So, a strong alkali is one that's super efficient at breaking apart, or ionizing, in water. The more completely it splits apart and releases those OH- ions, the stronger it is. Simple as that. And this chart really lays it all out. On one side, you have your strong alkalis, like sodium hydroxide. They ionize fully. That means every single molecule dissolves and pops off a hydroxide ion. Every single one. But then you look at a weak alkali, like ammonia. It only ionizes partially. That means only a few of its molecules are actually releasing hydroxide ions at any given time. So if you remember one thing, remember this. Fully versus partially. That's the whole game. And this equation for ammonia shows you exactly what we mean by partially. See that weird-looking arrow, the one pointing both ways? That is a reversible arrow, and it is so important. It means the reaction is in equilibrium. It's going forward and backward at the same time. So while some ammonia molecules are turning into ions, other ions are bumping back into each other and turning back into ammonia. It's a constant back and forth. Okay, let's take all this theory and put it into action. We're going to look at a really important reaction that involves alkalis making ammonia gas. Now, this isn't just some random reaction we do in the lab for fun. This is a big deal. When you heat an alkali with something called an ammonium salt, you produce a new salt, water, and our target, ammonia gas. And why should you care? Well, because those ammonium salts are a key ingredient in fertilizers, the stuff that helps us grow enough food to feed everyone on the planet. So yeah, pretty important. So how do you know if you've actually made ammonia? Well, we can use its own alkaline nature against it in a way. You just take a piece of damp red litmus paper, hold it over the reaction, and if ammonia gas is there, it'll dissolve in that little bit of water and turn the paper blue. It's the perfect, simple test.
Let's try building one of these equations from scratch, step by step. First up, we need our ingredients, right? Our reactants. In this case, we're starting with our alkali, which is lithium hydroxide, and our ammonium salt, ammonium sulfate.
Okay, step 2. What do we get? What are the products? The easiest way to think about this is like the ions are swapping dance partners. The lithium from the alkali grabs the sulfate from the salt, and they form lithium sulfate. Then, everything that's left over just kind of rearranges itself to make our other two products, which are always the same in this reaction, ammonia and water.
And there you have it, the full, balanced chemical equation. See those big numbers in front? Those are our coefficients. They're just there to make sure we don't break the rules of chemistry. You gotta have the same number of each type of atom on the left side as you do on the right. This equation tells you the whole story.
Okay. Awesome job, everyone. That was a ton of chemistry. So let's just take a second and quickly run through the most important takeaways from all that.
All right, pop quiz time. First question. What's the main thing that determines if an alkali is strong or weak? Think about it for a second. It's all about the degree of ionization, right? How completely it splits apart in water.
Okay, question number 2. Let's say you're in the lab. A mystery gas is produced, and it turns your damp red litmus paper blue. What gas is it? Yep, you got it. It has to be ammonia. So let's just lock these 4 key facts into our brains. Number 1, an alkali is just a base that can dissolve in water. Easy enough. Number 2, strength is all about ionization. Strong means it fully ionizes, weak means it only partially ionizes. Number 3, alkalis plus ammonium salts gives you ammonia gas. And number 4, how do you test for that ammonia? Damp red litmus paper turns blue. Got it? Good.
And that wraps up our explainer on bases and alkalis. So I'll leave you with one final thought to chew on. We talked about how important they are for making fertilizer, right? But what about in your own home or in big factories? Now that you get the chemistry behind them, start looking around. Where else do you see strong and weak alkalis making things happen in the world? Think about it.